z negative y. So let's have it with a different color. So this is 0z and negative y. And these are the vector fields that we live with a long time. They are tangent to the sphere everywhere, okay? This guy on the other plane. Okay. And I want to compute the derivative of y with respect to x, and you're suggesting to use the Euclidean definition in your coordinates. Okay, that's fine. Let's try to do it. So in my coordinates, I need a coordinate first of all, because this is written in 3 dimensions. This is a 2-dimensional manifold. I need a coordinate map. So you can do whatever you like, stereographic projection or just regular projection to prevent any confusion. So I'm going to project. So phi 1 is the projection from the upper hemisphere on the xy plane. So now my x in coordinates, I'm going to go with x1. How do you determine x1 in coordinates? Anybody can tell me? So this is x in 3 dimensions. This is phi that takes 3 dimensions to 2 dimensions, your coordinates. And I want to write my x1 in the 2 dimensions coordinates. How do you do it? Again, yeah, it's exactly the phi 1 star times x, right? Which is simply just take the x and y coordinates. So this is y negative x, that's easy. What about y? So here is y. y1 is the same, it's phi 1 star times y. Take the x and y coordinates, so it's 0 and z, but z now in the xy is like this, right? So do the Jacobian and it will come out naturally like this, but because it's projection, I can do it easily. Okay, I got x1 and y1. Apply this computation in coordinates. So partial y1, partial your q's. My q's now are just x and y, right? And now multiplied by x1, the result will be the 0 vector. That's okay, maybe really indeed 0, and we need to do it in another coordinate chart that overlap with this guy and see what we get. So I will do phi 2 now. So we are here in the upper hemisphere. Let's take a part that overlaps. I will take the overlap between the upper hemisphere and the right hemisphere. So phi 2 is now projection from the right hemisphere on xz plane. And you do the same, you get your x2, phi 2 star times x, which is the x and z, so this is 1 minus x squared minus z squared, and 0, you get y2, again it's the Jacobian, or the x and z coordinates, so 0 and negative 1 minus x squared minus z squared, and you do the computations in the x and z, so we do here partial y2, partial your q, and your q now are just x and z, right? And I will multiply by x2, and here is the result, it's x. Okay, so I did the computation in coordinates. Here I got 0 vector, here I got this vector, and note that we have a relation between these 2 coordinates, right? So I should be able to use its push forward to relate these 2 vectors. And again, there is no linear transformation that can take this guy to the non-zero vector here. So again here, there is no linear transformation. So this animal, the partial y, partial coordinates times x, this guy, this wave computation, doesn't transform well under coordinates. Simply, it doesn't live in the tangent space. If anything in the tangent space, any intrinsic vector must transform well under change of coordinates. If it doesn't transform well, it means that it doesn't live in the tangent space, and vice versa. So no linear transformation that does this job for you here. And I'll give you another reason to motivate what we can do. Actually, like I said, this doesn't work because it doesn't live in the tangent space. So even if you do this computation in the ambient space, so in the ambient, even in the ambient space, what do you mean the ambient space? This is S2, it lives in R3, and I gave you the vector fields in R3. This is three-dimensional. Do the computation here in R3. Well, okay, let's do the computation in R3. So partial y, partial q, now my q are x, y, and z, times the x's. This is what I will get, 0, 0, x. And here is 0, 0, x. This is your sphere. So this is x, y, and z. This guy is it's tangent here, but anywhere else, many other places, it's actually coming out of the surface. So it's not tangent. This is not tangent. Okay? So you start with two tangent vectors. I get a vector that is not tangent. Remember, we in differential geometry, we should any vector that is not tangent, we should not even see it. It doesn't exist. We don't see the outside world. Okay, so a vector that is not tangent, it's not a vector for us. So when I differentiate a vector with respect to another vector, I'm expecting the result to be a vector. When I say just merely by saying a vector, I mean it's tangent for sure. So this guy doesn't work. Okay, the way that we do it in Euclidean coordinates. And as an engineer, when you see this, can you suggest a way to define this element that we're looking for? Nabla x, y. Given two vectors that are tangent to the manifold. And as an engineer, I would see the manifold as embedded in hard dimensional, right? It's just a surface for us as engineers. So this is your manifold M, and this is a hard dimensional Euclidean space Rn. Okay? Obviously, n is larger than this guy. So can you give me a way? So what was the problem with this definition? Just the last problem is that when you do it in the ambient space, you get a vector that is not tangent, right? Okay, can you, from your engineering perspective, how can you modify this definition, partial q times x, to get me a tangent vector, right? If this is all what you need, okay, I can do it for you from an engineering perspective, which is, of course, mathematical perspective as well, but we are used to it most of the time. Any suggestion? How do you define this guy? In your perspective. If I want to do the derivative and stick to the tangency.
Project it in the tangent.
Say that again?
If you project it in the tangent.
Yep, exactly. So we will do this guy, partial y, partial, oh sorry, let's do here. So in this Rn, we are privileged. Why? Well, we have too many animals that I can use. I have my gradient. I have a dot product, which means if you have a dot product, I can define the normal. Why? Because by definition, the normal will be the dot product between this vector and all the vectors in your tangent space at the point vanishes. And I have a way of writing the dot product. Okay, so I can define these three angles. I will use the first here, x, y, that unfortunately will result in a not tangent thing. I will subtract the normal component. What's the normal component? Can you give it to me? What's the normal component?
Dot product between this and
So the dot product between this guy, whatever it is, and the unit normal, which I can define very well, and then in the direction of the normal. Indeed, this is the definition that the differential geometers propose. But it depends on the embedding. So here, it heavily relies on the embedding. This is along the early lines of Christoffel and Levi-Civita. It's very similar, very, very similar. But it relies on the embedding. I borrowed too many things from the embedding. I borrowed this guy, and the normal. We want to do it exactly the same, but intrinsic. So we want to do it without resorting Remember, actually, in the early construction, was if this is n dimension, this will be n plus 1 over 2. So say here, this is 5 dimension. You have a 5-dimensional manifold. Let's compute this guy. So you have 25 plus 5, so this is 30 divided by this is 15. So to do computations in a 5-dimensional manifold, you need to do it in 15-dimensional space. This is really, it's not efficient, right?
Is it Whitney speed?
No, it's well, I want the right. The Whitney embedding theorem says that this guy can be embedded in just double. Double is better than what I said. But the early constructions by Christopher and David Civita, it was for n squared plus n over 2. So this is really, and even if it's 2n, so if this is 5, I have to do it in 10. It's bad, right? So we need to focus on our manifold. This is the essence of differential geometry that you asked about very early on. Why would we want to do it on the manifold? Because it's much more efficient. Okay? So we want to do it intrinsically. It's the exact same definition. I will not flee from it. It's the exact same thing. Okay? I will not do anything new. It's this guy, but I'm going to correct. Okay? So want to do it intrinsically. So like anything in mathematics, we will start with some basic definitions, basic properties of what you want to achieve. So what you want? I want to create this animal that takes two vectors, not necessarily vector fields, okay? But they are vectors, and return a vector. That satisfies whatever properties you like. First, well, I want to define derivative of this guy with respect to that guy. So the differentiation is linear. So it's R linear in both, right? X and Y. So if you multiply any X and Y by a number, it gets out. If you have Y1 and Y2, you just add the same for X. Second, which is an important property, now I am stressing the fact that X is not differentiated. So if I multiply here by a function, the function must come out and nothing happens. Okay? For all f in C infinity. Any question about that? Yeah. And likewise, it's indeed y that is being differentiated. So if the f comes to y, now, yes, it will come out, but I will have an additional term, right? The product rule, which is the lead derivative of f along x, this is a scalar in the direction of y, for all f in C infinity. This really makes all sense for the animal that we want to create. If we want to really define a directional derivative of this guy with respect to that guy, this is what we are expecting. This is what we need. Okay? And just from these definitions, and we can come back and add later if we wanted to, or we can come back and remove one of this if it's unnecessary. But turns out that these are really sufficient. So this is the definition of.
So the third property was that, do we want that? You said we didn't want it in the lead, right?
No, we don't want it in x. This is the function in y. So this is the definition, what I just wrote here. This is the definition of a covariant derivative, the derivative that we're seeking. And sometimes, many times, we give it the name linear, because it's linear, connection. And you know that where the name comes from, right? Because it really connects nearby tangent spaces. Sometimes people say affine. So they use linear and affine synonymously here. Okay? So whenever you see connection, affine connection, linear connection, covariant derivative, they all have the same name. It's just the derivative of this guy with respect to that guy, abiding by the very natural definitions. And just by these definitions, you can prove right away the following lemma. It doesn't take any much at all. That, okay, given two vectors, x and y, I'm giving some points in M. So the result is a vector, right? So I can evaluate it as a point. Lives in the tangent space now. Okay, this depends on what? Does it depend on the values of y over the entire M or just locally? Does it depend on the values of x, the entire M, locally or just at the point? Okay, you can prove immediately that it depends on the values of y over just a small neighborhood, just a very small neighborhood. U is a neighborhood of P. So we don't need y to be defined everywhere, just define it locally around the point that you're interested in. And for x, it is just x at the point only, obviously, right? Because you need the derivative of y, so I need y defined in the neighborhood in order to differentiate. In the direction of x, I'm just doing something like a dot product with respect to x at that point. I just need the value. To prove these guys, it suffices to say if x of p is 0, this guy is 0, right? And you can show this easily from these definitions. And the same here, if y is 0 in a small neighborhood around P and anything outside, this guy is 0, and the definition suffices. So, moreover, we can do the following. Another lemma, but I'll just not state it as a lemma. So, if we have x, this is a vector, right? So it's x1, x2, x3 as components. So we usually write it as xi times ei. I'm reminding you that these ei's are just the partial q or partial related x's, right? These are the unit vectors that span your tangent space. Strictly speaking, the I should be superscript, but I will not go tensor-wise. But I will not go through this. We're not introducing tensors in this course. So I'll be sloppy with the indices. Okay, so I have here summation. And I will drop all the summations afterwards. So I equals 1 to n, and the same for y. So y also is the summation some components in these directions. So it turns out that actually it suffices to define how these guys, how ei and ej's differentiate with respect to each other, and this completes everything. So if you tell me how you differentiate some ej with respect to ei, by linearity, I can tell you how to differentiate any vector with respect to another vector, because they are just linear combination of these ei's, and the thing is linear. I'm going to add, just add. So if you tell me this, okay, so let's see, what is this? Go and figure it out, please. Go and do it in the 10th dimension, whatever. Do it the hard way, and just get these combinations. How each unit vector differentiate with respect to the other, and the result of, say, this is E1 and E2. The result is a vector, right? So it has components from E1 up to En. So the result is a vector, and I'm giving you the Ek component, okay? This Ek component is function of your coordinates. And these guys, we're going to give it the name, the very famous name, which is very famous in differential geometry and general relativity and Christoffel symbols. Okay? So